All right, lecture 64, terminal velocity. So we're going to extend our discussion of friction today by talking about a special kind of friction called drag. This results also known as air resistance. Okay.
All right.
So let's consider the following first, though. Let's consider an airplane at roughly, I'll say that the displacement from the ground is 6,400 feet. Okay. And this is, on Earth, we'll assume that the gravitational acceleration is constant at this altitude. You probably remember the equation that bypasses time of flight and gives us the velocity in terms of the displacement and the acceleration, right? If v squared is equal to v naught squared plus 2 times the acceleration times the displacement, right?
Yeah.
So we can substitute in these values. I want to know, how fast is this guy going when he hits the ground? Let's say he jumps out of his airplane and he forgot his parachute. Okay? It's kind of a dumb mistake, but it can happen. Maybe his parachute failed. I don't know. Nonetheless, though, we want to calculate what's his velocity by the time he hits the ground. Maybe he can survive. So let's see. So we need to put in. Well, let's say the initial velocity is 0. Okay, because there's no reason to get a running start. So that's going to go away, right? Then we'll get v squared equals, well, a is going to be minus g, okay? So we'll call this minus 2g, and then 6,400 feet is the altitude that we're jumping from, so that's the distance we're going to travel, okay? G, of course, is, let me just rewrite this. G is 32 feet per second squared, you might recall. Yes? So I'm just going to move the numbers around a little bit. Instead of this being 32, or 64, I'm going to make this 32, and I'll make this 4. You see I'm just moving the numbers around a little bit, right?
Yeah.
So we have to take a square root, so we're going to get the square root of, and this should be, of course, positive. We can't take square roots of negative numbers. 2 squared times 32 squared, and then the hundreds will be 10 squared, right?
Yeah.
So this number 4 times 32 times 3,200, well, 3,200 is just 32 times 100. So 100 is 10 squared, 32 times 32 is just 32 squared, and 4 is just 2 squared. That means that our velocity is 2 times 32 times 10, which is 640, I'll put the units in now, feet per second, okay?
All right.
So that sounds fast, 640 feet every second, but let's convert it over to miles per hour, which we know a little bit better. So maybe it's not that bad, maybe it's going to be like 20 miles per hour. I think we could handle a fall at 20 miles per hour. Let's see. Let's convert that, 640 feet per second, times, of course, we'll have 3,600 seconds per hour. That'll change the seconds into hours in our rate. And there are, 1 mile is 5,280 feet. I think that's right. And if you punch this into the calculator, let's see here, hang on. Yeah, it didn't look good. 436 miles per hour. Now, do you think that's true? Do you think if I jump out of an airplane at 6,400 feet, that my body's going to be traveling 436 miles per hour right before I hit the ground? No, it's not, right?
Yeah.
It's going to slow down fairly considerably because of air resistance, right? I mean, because if this was absolute, right, then that means that even with my parachute, right, even with my parachute, right, there's nothing in this equation that says I hit the ground at any slower speed, right?
Yeah.
So something must be happening to the acceleration, okay? So let's have a look and see what that is. So there is a force called drag, I'll call it F sub d, and it is equal to b times the velocity to the nth power, okay? Sometimes n is 1, sometimes n is 2. It depends on how fast you're going, on which of these forces, what the correct form of the force should be. Okay? The sign of b, however, will always be the opposite of the sign of the velocity. This is a force which is always acting in the opposite direction that you're moving. Okay?
All right.
You're not going to get a boost from behind because of drag. Right? Drag is literally dragging. Right? It's trying to drag you in the opposite direction that you're moving.
All right.
It's only present, however, when you are actually moving. That's what the velocity dependence is all about. So if I were to write, let's draw our little guy. Here he is all splayed out in free fall, right? he's got, of course, his weight.
Yeah.
It's minus mg if we choose up as the positive direction. And then opposing him will be this drag force. Okay? And so if we write the sum of the forces for this, what are we going to have? We're going to have the drag force in the positive direction. So we'll write b v to the n. And then the weight minus mg in the negative direction. Okay?
All right.
And this is going to be equal to the mass times the acceleration. Now, we could handle the simple case when the acceleration was a constant, right? If this was gone, this is just ma equals minus mg, right? A is equal to g. The constant acceleration is an easy problem to solve. That's the one we've dealt with the most, okay? But if we include air resistance, or drag, then it becomes a little more complicated, and we're not going to be able to solve it, just so you know. This is something you can do once you have calculus under your belt, okay? We'll be able to solve it then, but we will solve an easier version of it here at the end of the lesson without using calculus, but we're going to cheat a little bit. So at t equals 0, right? At t equals 0, the velocity is equal to 0. I said we had no initial velocity, right? So our velocity will be 0, which means the drag is 0, which means we just have the acceleration due to gravity, yes?
Yeah.
And then as time goes on, this velocity is going to increase, and at some point, this force of drag will be equal to your weight, and the acceleration will become 0.
All right.
So if we were to like graph this and say, what's this look like? We would see, here's time, here's our velocity. We start out, well actually we start out at 0 velocity. Let me think about this a second. Yeah. We start out at 0 velocity, so I don't need that. So we start out down here at 0 velocity, right? And we start off initially, I'm not sure if that's the best way. Let's do it like this. We can approximate this by a straight line. I'm just going to extend this straight line all the way up. This is that constant acceleration due to gravity, right? This is just mg, so to speak. All right? And if we call the speed that we're traveling when this is equal to this, right?
Yeah.
And when the acceleration then becomes 0, right? So that's, we've got this notion, we'll call it the terminal velocity. Okay? So this happens when bv to the n is equal to m times g, such that they cancel completely, so our acceleration becomes 0, right? We'll call that the terminal velocity. I'm just gonna denote it here. V sub t, okay? And so we'll draw it as a dotted line across here. This is basically an asymptote, right? So we're going to approach that terminal velocity. And it's going to cause this graph to stop going in a straight line and asymptotically approach this terminal velocity, okay?
All right.
So what is this terminal velocity? Well, if you took this line that we have here, whose slope is g, right? Is that right? I think that's right. Times this tc. So at some time, which we'll call this point right here, too many dotted lines, I think. Let's stop with the dotted lines, and we'll just show this. We'll call it the critical or the characteristic time, t sub c. It's this point right here where this dotted line crosses this flat horizontal line we call the terminal velocity. So if I take g, the slope of this line, times tc, this will be equal to the terminal velocity. And I guess I could solve for the terminal velocity over here, right? And say that vt, because this is the condition when it's set, right? So this is really v sub t. Vt will equal m over b times g, and we'll take the nth root of that. Since it's an equation of b is raised to the nth power, we're going to take the nth root, okay?
All right.
But characteristically, that's what's going on, okay? We're going to approach some velocity, and we will never exceed that velocity. We'll kind of approach it asymptotically. And this is the point we'll no longer experience an acceleration. We'll be traveling at a constant velocity, but not experiencing any acceleration, okay? So what role does this b play in things? Well, if b is large, right, that makes this force large,
Yeah.
which means that it's going to be able to be equal to mg, your weight, much quicker, right? The velocity v does not have to be as big for bv to the n to be equal to mg, right?
Yeah.
So a large value of b, this is like your drag coefficient, okay?
Okay.
So a parachute would have a large value of b, whereas a fighter jet, which is designed to be aerodynamic, is designed to have a very small value of b. So it doesn't have a lot of drag as it moves through the air. That way it can go faster and more fuel efficiently and whatnot, yes?
Yes.
Sports cars, the way they look, they're designed such that air flows over them easily,
Yeah.
and thereby minimizing drag. You can imagine if I had a car that had a sail on it, it would be hard to get that car to go very fast because the sail would be slowing me down, yes?
Yes.
Now I want to consider a much simpler situation where there's no acceleration at all, okay?
All right.
Okay, so imagine that you've created some kind of vehicle, right, and you're going to drive it up to a certain speed, and you want it to coast as long as it can, okay?
Yeah. All right.
So we want to model that situation. All right, so we have a particle, which we're going to use to model our coaster, that's traveling some initial velocity v naught, and it's not no accelerations involved. It's traveling across a very slick, frictionless surface, but we still have air, so there's going to be wind air resistance, right, creating drag and slowing us down.
Yeah.
So to make things simple, we're going to assume that n, the exponent for our drag, is 1. So it's just proportional to the velocity. So the drag is proportional to the velocity, and of course times b, some coefficient that gives me, how aerodynamic I've designed my vehicle or particle in this question.
Yeah.
So what do the sum of the forces look like? Well, the sum of the forces are equal to minus bv. That's the only force,
Yeah.
because we're just coasting. We're not in. We're traveling parallel to gravity, so the gravitational field is not affecting our motion in that direction. So we basically are in a gravity-free zone. And this will be equal to the mass times the acceleration. So here's our singular force. Here's our Newton's law, second law. So we can write, what is acceleration? Well, that's delta v over delta t, yes?
Yeah.
That is going to be equal to, I'll divide out m on both sides, and we get minus b over m times v. Okay?
All right.
So this is the equation that we have to deal with. It's as simple as we can possibly get them. However, calculus takes this down in a heartbeat easily. Okay, but we don't have calculus at our disposal, so we have to find another way. Let's talk about it qualitatively for a minute first, though. Okay?
All right.
So let's do another graph of velocity versus time. At t equals 0, we start out at some initial velocity called v naught. If we didn't have this drag force, right, then we can imagine just traveling in a nice straight line. Sorry, that's not correct. What I said is not right. Let me say that again. All right. So initially, our velocity is v naught, right?
Yeah.
So just right over here. Initially, the acceleration, right? A. Well, let me just write it as delta v over delta t again. Delta v over delta t is equal to minus b over m times v, but our velocity initially is v naught, right? So times v naught. So this dotted line that I've drawn here, right, is a line that has a slope of, slope of minus b times v naught over m. Okay?
Yeah.
That's the slope of that line. And we're going to use as our characteristic time, it's just some quantity, right? So I can get rid of all these b's and b's and m's and stuff, okay?
Okay.
We're going to write a characteristic time which coincides with when, at this constant acceleration, this initial acceleration, we would reach v equals 0, right? So as we have it now, the velocity as a function of time is going to be equal to the initial velocity minus b over m, v naught over m times the time. So that's for the dotted line, okay? That's not for this, it's just for this dotted line. So that's if we were decelerating with that initial acceleration that we experienced, okay? And so you can see that v of 0, right, is just equal to v naught because t equals 0. And v of this critical time is equal to v naught minus b times v naught over m times the critical time, and that is equal to 0. Because I'm defining this, not critical time. I'm defining this characteristic time as the time at which, at this initial acceleration, our velocity is equal to 0. That's the characteristic time. Okay? Does that make sense?
Yes.
Okay. So when is that the case? Well, all I have to do is solve for Tc. And Tc is then equal to, the V naughts will cancel, it'll just be m over b. Okay? So that's going to be a useful expression. What I'm going to do now is I'm going to manipulate this. Okay? So let's first note, I can rewrite this as delta V is equal to minus b over m times v times delta t. Yes?
Yeah.
And I can use this critical time that I've introduced over here, right? I keep saying critical time, I mean characteristic time. So if you hear me say critical time, I must be thinking of, I think with the last lecture we had something that was a critical angle, right?
Yes.
Yeah. So this is characteristic time. I'm going to introduce this characteristic time into this equation, right? So nothing has changed. This is still just this equation, but I can rewrite it as delta V is equal to minus delta t over this characteristic time times the velocity. Okay?
All right.
It's just a little algebra and introducing this characteristic time into the equations. Well, what is delta V? Well, let's discretize it. Let's think about it. I'm going to basically break time up into some little tiny chunks. Okay?
Yeah.
Always the same size. It could be 1 second chunks. It could be half a second chunks. It just depends on the context. So I'm going to fix delta t. Delta t is fixed. So when I discretize this, right, delta V becomes equal to V sub I minus V sub I minus 1. These we call time steps, right? I think we talked about this in some detail when we talked about the rocket equation. Okay? So the change in the velocity is equal to the velocity at the current time step minus the velocity at the previous time step. How much have we changed in those little time steps? How big is a time step? It's exactly delta t. Okay?
All right.
I want to know what the time is. How many time steps have I taken? Multiply times delta t, right? So t is equal to n times delta t. Right? So my time step is 1 second. If I've taken 10 time steps, 10 times 1 is 10 seconds. You see?
Yeah.
So that's what delta V is. So I'm going to introduce this into this equation up here. So we have that Vi minus Vi minus 1. These are subscript, right? V sub I minus V sub I minus 1 is equal to minus delta t over Tc times V sub I minus 1. Now, of course, it may not be obvious that this should be V sub I minus 1 and not V sub I, but again, I want to solve for V sub I. So I'm going to take this velocity to be the velocity of the previous time step. Okay?
Okay.
And if I do that, I get that V sub I is equal to V sub I minus 1 minus delta t over Tc times V sub I minus 1. But see, both of these have a V sub I minus 1 in them, so I can rewrite that as V sub I equals V sub I minus 1 times 1 minus delta t over Tc all times, well, that's it. All times nothing, or multiply times that, yes?
Yep.
So here's my equation, okay? So I think maybe what we do at this point is we just look at some values, right? So we know initially our velocity is V naught, right?
Yeah.
Yeah?
Yep.
Well, what is V sub 1? That's the, after delta t amount of time, it's the first time step. What's it equal to? Well, it's equal to V sub I minus 1. Well, what is I minus 1? Well, I is 1, so 1 minus 1 is 0, so this is equal to V naught times 1 minus delta t over the critical or characteristic time. Yes?
Yeah.
All right. Let's get, what's the velocity after time step 2? Well, V sub 2 is equal to V sub 1, because if I is equal to 2, then I minus 1 is equal to 2 minus 1, or 1, times 1 minus delta t over t sub c. Yes?
Yeah.
But we know what V sub 1 is, right?
Yeah.
V sub 1 is just this up here, right?
Yeah.
It's equal to V naught times this quantity here. This quantity is not changing, right? So this is just equal to V naught times the quantity 1 minus delta t over Tc squared. That's interesting, right?
Yeah.
And if we were to continue on and get V sub 3 and V sub 4 and go all the way up to, V sub n, we would see this is just equal to V naught times 1 minus delta t over T sub c to the nth power. Okay?
All right.
Does that make sense?
Yes.
You can see that that's happening. Each time we increase the time step, we take the previous value, the previous velocity, times this constant, 1 minus delta t over tc, right?
Yep.
Remember, delta t is fixed. It's just, we've set it equal to some value, like 1. Okay? The characteristic time we got, by looking at, we assume we have the initial acceleration, the initial acceleration, right? How long before our velocity is 0? That's the characteristic time, yeah?
Yeah.
So all of these values in here are constants, yes?
Yeah.
And so we end up with this. And this should remind us of something, right? We learn, or you learn, rather, about compound interest in, a standard pre-calculus course. Compound interest, right? The equation is, well, my account balance A is equal to the principal, the initial amount I deposit in the account, times 1 plus the yearly interest rate divided by the number of compounding periods per year, raised to the m times t power, right?
Yeah.
And then if we allow the number of compounding periods to go to infinity, right, that's called continuous compounding, then A becomes equal to P times e to the RT. You guys remember that?
Yes.
Yeah. So the form of this equation and this equation are very similar, right? And so I think it's not much of a stretch to reason, right, that in the limit that delta t becomes very small, right,
Yeah.
towards an infinitesimal size, that we can make an approximation, that we can make the leap, the same leap that was made with compound interest, right, and write this as the velocity is equal to, let me write the velocity as a function of time, the velocity as a function of time is equal to the initial velocity times e to the minus, why minus? Well, because of this negative sign right here. This was positive, remember, right? Here we have a negative sign. E to the minus t over t sub c. And if we graph that with our graphing calculator, or just plug some values in, we'll see that it'll start out at b naught, just like we did, right? And then it's going to decay asymptotically down towards 0. And it'll ultimately bring us to a stop, okay?
Okay.
So with calculus, we would have gone to this equation immediately after writing this, okay? It's about as easy a differential equation as they come. I can't think of an easier one, to be honest. And we got there by making an analogy to compound interest, okay?
Okay.
I thought about going into some detail on showing why this goes from here to here, but I could not think of a way to do it without drawing upon what are probably foreign and unfamiliar topics like Taylor series expansions and stuff like that. So there may be a way to do it, and anybody knows of a way, then you can put that in the comment section of the video. But I think since everyone's probably experienced compound interest, right, they can probably make this leap and not be too concerned about it, okay?
All right.
So that is air resistance, or drag. Is there anything else I want to say? No? And I think that is all I have to say about this topic. So we'll move on to one last problem in where we deal with angular momentum. Remember, we did friction as kind of a sideline issue, because in this last problem from angular momentum I want to consider, which is, we're going to basically finish up all we're going to say in this course about statics, right? We need friction in order to do that. So we're going to deal with the sliding ladder problem, right? How high can you climb up a ladder before it becomes unsafe, essentially? And so that'll be the topic of the next lesson. And then we'll move on to Kepler and Newton's gravity. All right, that's it.